I promise you there's a logic to me being back up here. You're not going to hear from me the next 2 days back to back on presentations. And I get to give this presentation on behalf of a broader team that has come together to partner on a small project that looks at what have we accomplished over the past year in terms of concrete tie research, and pull it together into discussing what are the lessons learned and where do we go from here in terms of the needs within the industry. So this is a preliminary presentation that shows you a few of these high-level findings. One thing I will mention right off the bat is the majority of this presentation content was pulled together by Josue Bastos. Josue was our PhD student here. You probably remember him, many of you that were around here, and he is down at MRS in Brazil and is one of their lead research folks down there. This project is a partnership between Illinois, Kansas State, and the University of South Carolina. So specifically Bob Peterman at Kansas State, Demetrius Rizos, and Yu Chen at South Carolina. So as I go through this presentation today, I want you to please take note. And I know I'm going to hear about this because you all are not bashful. This is an attempt to be an encyclopedic capture of what's happened in the past 10 years. It will probably fall short of that. So please, at breaks, come up to me and say, hey, you forgot such and such research. It was really impactful and it should be added to your list, because ultimately this is going to turn into a comprehensive literature review paper that is going to summarize what we've been up to in the last 10 years. So whenever people come up to you, those of you that work in concrete ties, and say, what has happened? You know, where has the industry gone recently? How far have they come? You get to give them this paper, and 3 hours later, they emerge as an expert. So here's the outline of the presentation, a little brief background, some advancements on the design side, talk about some of the research toward failure modes, and then a few future steps remarks. So one of the things that you may or may not know if you're not involved with concrete ties on a daily basis is these are post-tension or pre-stressed objects. And when we look at those, there's a variety of ways in which we both design them and we think about their function. So we have a couple of different ways in which we pre-stress the object, the tie. And we do this so we can resist the typical bending modes that are applied out in the field. So the sources of stress that we use to place the concrete in compression, the first one we're trying to resist against is an external moment. So we have the pesky train that comes by, high wheel loads, and they induce bending. So that's the top level of stresses up there. And we are trying to overcome those, at least in that case, in terms of center bending, we're trying to overcome those stresses by two forms of pre-compression. One of them is just the pre-compression of the wires that run through the tie. That's that center stress term. And then at the bottom, what is unique about the way in which we design concrete ties is we design an internal moment into the tie. We have a pre-stress eccentricity. There's a difference between where the centroid of our steel and the centroid of the concrete is. So we create an internal moment to resist the most prevalent bending modes that is out there with the tie. It's out there in the field. And in terms of design, what we're thinking about is we're summing all of these up, and we're trying to avoid a tensile failure in the top surface in terms of center bending, or a compressive failure in the bottom. So this again is a center bending example. And we have ways that we can estimate the tensile and the compressive strength of the concrete. So everything that we talk about with concrete ties, it's based on, it goes back to kind of the fundamentals of pre-stressing. One of the things that we've done over the past decade is we have captured a lot of really good data out in the field on the demand side. So we've captured data on a variety of modes, looking at what are the demands that are actually placed on the ties, because this is something that was not well understood historically. The demand, we understand the capacity, and we've done some additional work here on ultimate capacity, but we understand first crack capacity quite well, especially those of you all that are the suppliers. But one of the things that we wanted to add was understanding what's the demand out there in the field. So a lot of those dots on the map that I showed you earlier correspond to sites in which we had surface strain gauges and collected data on tie bending. And you can see significant variability among the different modes. And this is not necessarily surprising to you all, but it's data that largely we did not have or consider in the design process prior. We've seen a lot of failure modes, and we want to keep these in mind as we turn down the lights some more. We want to keep these in mind as we go through any research process or a design process. We should be considering these. So we have bottom abrasion, end splitting, rail seat deterioration. That was a big topic 10 years ago that we invested a lot of time in, center cracking, and then some debonding along the prestress strand. So these are failure modes that hopefully we have begun to address through some of the research that's been funded over the past 10 years. So here's a couple of advancements on the design side. One of the things that we did early on and that we are passionate about are sending ballots through ARIMA, specifically Chapter 30, to improve the content in there. And as many of you all understand in this room, it's a slow process. It takes time, and rightfully so. We have to spend time with the students refining the ballots and improving upon them. One of the early ballots that we worked on here at Illinois, and it was led by a student named Henry Wolf, was an attempt to get us further up the curve in terms of the sophistication in which we estimate bending moments for the tie. So when you go to ARIMA Chapter 30 now, you see equations like this. It didn't used to be like that, but these are ways in which we can more quantitatively come up with accurate bending moment estimations based on axle loads. And it brought us in closer alignment with the EN, as that last bullet point says. We've also seen a lot of unique tie designs emerge worldwide with a variety of different applications associated with them. And some of these you'll see in the literature and you can learn more about. And I'm going to hit a few of them later in this presentation, but we've seen more ties that have been produced internationally for energy harvesting. We've seen some work here domestically from Nortrack in terms of interspersing ties and from Rockla as well on that, a renewed interest in that area. And then one of the things that we like to do here is we like to turn the ties into an instrument in and of themselves. So we've seen that both kind of experimentally here at Illinois and more in production fashion worldwide. We've also noticed that there's started to be a change toward a more performance-based method of specifying concrete ties. So we've typically been quite prescriptive, and we are trying to encourage a more performance-based. We've seen examples elsewhere of this being successful, and you can see up here, I won't spend a tremendous amount of time on the differences between these two, but in terms of engineering and considering risk, this is something that we've really tried to encourage the pursuit of, and this is part of a project that some of us have been working on together. And it's a part of actually a larger design paradigm that we've been talking about here at Illinois, which is mechanistic-empirical design. And we know that the pavement community, those of you that are familiar with it, are well-versed in mechanistic-empirical pavement design through using the MEPDG. And one of the things that we're trying to do is to get more advanced on the rail side by thinking more intelligently about how we design some of these components, assessing what the stresses are, thinking about those failure modes, and then designing components around them, as opposed to kind of our traditional process we tend to go through, which is an iterative process of try our best to make it bigger and better and do some lab testing and see whether or not it passes certain thresholds. But we think there could be a better way. In terms of addressing those failure modes that I showed earlier, there's been a variety of research. One exciting project that's taken place over the past decade has been led by Professor Rizos at the University of South Carolina. His high-strength reduced modulus concrete ties and the way in which they can change the cracking patterns here in this building. For several years, Professor David Lang worked on fiber-reinforced ties, and you can see in those images at the bottom in terms of the crack arrest capabilities of fibers. That was some work that we did. Some amazingly impactful work that has really impacted our industry and impacted Chapter 30 is work that's been led by Dr. Peterman out at Kansas State University. You're going to hear more about this later, even before lunch. So I'm not going to go into great detail other than saying it's been fascinating to be an observer to the work that's gone on led by Professor Peterman, but also engaging Professor Terry Beck, and a whole host of grad students. I don't know how many people total you've had out there, but the work that they have done to come up with tests for mitigation of splitting resistance on the end of the ties, coming up with a novel metric of byte per length. He's one of the few people I know that can combine units of measure into a single metric from SI and US units. There's also been significant progress in the area of freeze-thaw durability. This is work that's been led by Professor Kyle Riding, now at University of Florida, and David Lang, who's retired, Professor Emeritus here from University of Illinois. We've seen their deep dive into both rheology and just the viscosity of concrete, and looking at how we can better create samples that map to what's going on in the form. So they came up with methodologies of how we can we can make samples and attach them to vibrating forms when we're manufacturing ties, and improve the way in which we think about vibration and think about testing ties for freeze-thaw durability. Rail seat deterioration, as I said, 10 years ago, this was a big topic of conversation. We had a lot of presentations at events like this. We even had special events. Those of you that were out in Denver, Colorado for the RSD event that we hosted out there. We spent a lot of time, here's the names of all the graduate students on the bottom that worked on rail seat deterioration and trying to mitigate this failure mode. And one of the main things that I feel like changed in the pursuit of solutions to RSD was finally kind of an end of finger pointing between the tie people and the fastener people, and realizing it was a system level problem. And I think that there are things that we have done to really help mitigate RSD over the past 10 years. And we certainly understand the mechanisms that are listed up there a lot better. Some other work was led by Professor Peterman and Professor Riding related to under tie abrasion. They conducted a significant amount of field work by getting ties brought back from the field and conducting tests in their laboratory to understand the effect of bottom abraded ties and of different types of pre-stressing that was within those ties. And they quantified the remaining flexural capacity in those, and really good work. I was able to tour Bob's laboratory out in Kansas a couple of weeks ago. And then there are ways that we have been investigating how we can mitigate the abrasion on the bottom of the tie, not the least of which is under tie pads. Really exciting work too has occurred in the area of non-contact measurement. The top image up there is some of the digital image correlation work that's gone on at the University of South Carolina. They were tremendously encouraging to us here at Illinois, because we also followed in that line and did some DIC work. Kansas State developed the laser speckle imaging system, and it's exciting to get to see a couple of weeks ago the production version of that equipment at their kind of spinoff company there in Manhattan. So a really great outcome from the FRA funded research in terms of the laser speckle technology to look at transfer length. We've also tapped into the NDT community to try to harness some of their knowledge to try to apply it to assessing tie health. And a couple of the examples of this would be Paul Fisk's work from NDT Corp and the really good work that he did in terms of assessing concrete tie health. And also in this building, we have Professor John Popovics. He did some really great work and regarding fully non-contact measurement of ultrasonic assessment of ties. And this was funded by the AAR through the Technology Outreach Program. And then also we're seeing more and more machine vision, LiDAR systems, 3D laser scanning systems that have come about that allow us to further assess the health of cross ties. And we've been fortunate here at Illinois to get to partner on some of that work. So here's some of the future advancements I'm going to list. Smart cross ties. And in that smaller print up there, you all are obviously going to have copies of these presentations. But in the small print, Marcus and I were fortunate to partner with a researcher over in China. And we wrote a paper that was a review of smart sleepers. So we were amazed in writing that paper how many different applications there are for smart sleepers. But we've seen self-sensing concrete, self-healing concretes, any of the concrete advancements you've heard of. A lot of those are being applied to concrete ties. The bottom down there, I give credit to Professor Basamandraos. You're going to hear more about this, but he's done some really, really novel and visible work in terms of shape memory alloys and is a very gifted researcher. The hybrid prestress idea, this is something that Bob Peterman, one of his brainchilds, and something that we're still discussing, is taking advantage of the best of both worlds between pre-stressing and post-tensioning and seeing if a tie could be developed to take advantage of both of those. We also know that in the future, there's additional updates to ARIMA. I'm going to give 2 examples here. One of these is something that we talk about in committee meetings regarding shoulder locations and tolerances, and another is an area that has been largely devoid of research within ARIMA, which is the area of turnout ties, long concrete turnout ties. So we've got a whole list of things on Committee 30 that we want to advance, but there's just a couple of ideas there. Few conclusions. It's exciting to look back over the past 10 years. We've seen some notable advancements. And if anybody appreciates them, I hope it's this room. I'm not sure that I could go out on the street and get people excited about some of these advancements, but we all know we live in an industry that is all about incremental change. So I can look back over the past decade and see specific incremental changes that have been made that are a result of the funding and the trust that was placed in academics in this area. Some new design philosophies are coming on board, and we've seen some of these used. Some of the things that we've been talking about here, we've seen them applied to ties and on Amtrak, for instance. A lot of research on failure modes and understanding really the mechanisms and the modes behind the failures. Exciting new inspection technologies that have emerged that probably we wouldn't have been thinking about 10 years ago, sitting in this room, that show promise. And then finally, I can't say enough good things about the partnership that we have had in the industry. So first and foremost, to FRA for their vision for funding this program, and CAM to you specifically for funding all these universities and allowing us to work together as academics. Next to the suppliers, I have memories of Vince, I saw you over there. I have memories, Vince, of you all being willing on a holiday to let us come in and manufacture ties at one of your facilities, one of the CXT facilities. That type of partnership from the suppliers and then from the railroads for giving us your time to give us your advice and take us out on track and show us some of these problems. It's really, really been an impactful season. And you've allowed us to educate a generation of students, some of which are in this room, gainfully employed in the rail industry, thanks to that partnership and funding. So again, thanks. Here's my partnering universities here. We're grateful to get to work with South Carolina and K-State and some of our industry partners on the rail side and the supplier side. So again, if you weren't mentioned in there and if you've done something noteworthy, please don't be offended. Just come talk to me in the hallway. We want to make sure that you're included, and thanks. Well, we probably don't have time for questions, but thanks for your attention. And any questions on this? You're going to hear more about several of these technologies and the advancements later. So yeah, Steve. How close are you to be making some recommendations to the industry there? Yeah, that's close, right? I've sat in, I don't remember now, all the committee meetings blur together, but I know I've sat in a committee meeting and I've seen, I mean, the ballots are there, right? Kyle's ballots. Okay. And what is it in terms of the full scale test or match cure? How about one of the suppliers speak up to this? What you all have probably been vehemently excited or vehemently against some of these changes. Rusty, where are you, not to put you on the spot? Yeah. Okay. Logan, what's passed?
What's passed?
Yeah, what in terms of the freeze-thaw? I mean, I know on Professor Peterman's, in splitting and some of those topics, and I know where we stand on that. What's, to answer Steve's question, on the freeze-thaw side, what has been impacted in ARIMA?
I forget exactly. We did some updates a while ago, I think, to getting in line with ACI. Current requirements, but nothing recently.
Okay. Vince.
Yeah, those are my doubts.
Okay, sorry, Vince.
Was the Freeze-Thaw for addressing this airway spacing, bringing that into line with kind of some of what's going on in the Canadian market in terms of water cement ratio and air spacing, also the delayed estride formation, how to address those things with the current temperatures.
Balloted, passed, and in the manual. Thanks, Vince.
Thank you.
So many ballots. It's actually it's a continuum. It's a process. It involves patience and character transformation to get a ballot through the ARIMA process. We should proceed on it. Please approach me again. Approach me in the hall. Ask any questions. But again, most of the stuff that you saw there, it's not maybe 20% of it relates to what we've done here in Illinois, and the other 80% I'll be pointing to other experts in the field. So